So here in this question there are two parts. In the A part we are given that water flows through a shower at the rate of 10 liter per minute. So volume flow rate we are given as 10 liter per minute, and the density of water is 1 kg over liter, and the temperature is being increased from 16 degrees Celsius to 43 degrees Celsius by using electric resistance heater placed in the water pipe. So T1 is 16 degrees Celsius and T2 it becomes 43 degrees Celsius. So we have to calculate the amount of electric power that is required to increase this temperature and the entropy generated during the process in kilowatt over Kelvin. So to solve this problem we'll be requiring some one input data, that is the value of C. Specific heat of water is 4.18 kilojoule over kg Kelvin, and we have obtained this value from the table A3. Now first we will be calculating the mass flow rate of water, that is m dot is density into volume flow rate. So density we have 1 kg over liter times the volume flow rate is 10 liter per minute. So after solving this, we'll get the mass flow rate as 10 kg per minute. Or if we convert this thing into kg per second, so we'll get 1 by 6 kg over second. Now next, we'll be applying the energy balance equation on our system, that is open system in this case. So we have energy in minus energy out is equals to change in energy of the system. So this term would be 0 since it is a steady process, and energy in we have the work input, the power input, plus m dot hi, and energy out we can take this term to the right side, so energy out we have m dot h2. From here the work input or the power input will be equals to m dot h2 minus h1. I have taken m dot common. So the formula for h2 minus h1 is m dot cp t2 minus t1, or we can write c also because for water cp and cv is same. So m dot we have 1 by 6 kg per second times c we have 4.18 kilojoule over kg Kelvin times the temperature difference is T2 minus T1, that is 43 degrees Celsius minus 16 degrees Celsius. So we're going to solve this and we'll get the value of power input as 18.8 kilowatt. So this is the required power input. Now next we have to calculate the entropy generation. For that we will be applying the entropy balance equation on our system, that is a steady system. So entropy in, the rate of entropy in minus the rate of entropy out, plus the entropy generation is equals to change in entropy of the system. Now since the system is steady, so this term would be 0. So we have m dot s1, out we have m dot s2, plus entropy generation is equals to 0. From here entropy generation will be equals to m dot s2 minus s1, and which will be equals to m dot c natural log t2 divided by t1. So we have all the values, we can plug it here. M dot we have 1 by 6 kg over second times C we have 4.18 kilojoule over kg Kelvin times natural log T2 divided by T1. So T2 we have 43 degrees Celsius. So if we convert this thing into Kelvin, we'll get 316 Kelvin divided by 289 Kelvin. So we're going to solve this and we'll get the value as 0.0622 kilojoule, sorry, it is kilowatt over Kelvin. So this is the final answer for the entropy generation. Now next we will be solving the B part. Now in the B part, we are given that we are using the heat exchanger that has an efficiency of effectiveness of 0.5 to decrease the power consumption, and we are given that the warm water at temperature of 39 degrees Celsius. So temperature in the heat exchanger is given as 39 degrees Celsius is passed through the heat exchanger to preheat the incoming cold water. So this is the input data we are given. So first of all, we'll be calculating the amount of energy saved. This is the B part. Amount of energy saved, we have effectiveness times Q maximum. So the formula for Q maximum in this case is m dot C T maximum minus T minimum. So effectiveness we are given as 0.5 times m dot, we have 1 by 6 kg over second, times C we have 4.18 kilojoule over kg Kelvin. So T max here will be TH, that is 39 degrees Celsius, and T minimum we have 16 degrees Celsius. So we're going to solve this and we'll get the value as 8 kilowatt. So this is the amount of energy saved. So if we calculate the amount of required power input, so power input in the B part will be power input in the A part that we have calculated minus Q saved. So this value we have obtained as 18.8 kilowatt, and this one is 8 kilowatt. So after subtracting, we'll get 10.8 kilowatt. So this is the actual power input for the B part if we are using the heat exchanger that has an effectiveness of 0.5. Now next we'll be calculating the temperature outlet, basically the temperature of the water at the exit of the heat exchanger. For that we'll be using our heat exchanger as our control volume. So we can say that Q dot is equals to m dot C TC out minus TC in. So Q dot we have obtained as 8 kilowatt, and m dot we have 1 by 6 kg over second, and C we have 4.18 kilojoule over kg Kelvin. TC out we have to calculate, minus temperature in we have 16 degrees Celsius. We are taking these value in reference to the heat exchanger. So from here, temperature out from the heat exchanger will be 27.5 degrees Celsius, or if you convert this thing into Kelvin, so we'll get 300.5 Kelvin. Now from here we are increasing, we are giving power to increase its temperature from 27.5 degrees Celsius to 43 degrees Celsius. Initially what we are doing, we were increasing its temperature from 16 degrees Celsius to 43 degrees Celsius, but now in this case by using the effectiveness we just want to increase its temperature from 27.5 degrees Celsius to 43 degrees Celsius. That is why the power input has reduced. So now next we can calculate easily the entropy generation. So the entropy generation we have m dot C natural log T2 divided by T1. So m dot we have, let me write here, this is 1 by 6 kg over second, times C we have 4.18 kilojoule over kg Kelvin, times natural log T2 we have 43 degrees Celsius, that means 316 Kelvin, and T1 we have obtained as 300.5 Kelvin. So we'll get it as 0.0350 kilojoule over kilowatt, basically kilowatt over Kelvin. So if you calculate the entropy reduction, this is also the rate of entropy generation. So entropy reduction will be 0.0622 minus this one 0.0350. So we'll get 0.0272 kilowatt over Kelvin. So this much of entropy we are able to reduce if we are using the heat exchanger. So I hope you got the problem. Thank you.